Hi, and welcome to this section of the pre-algebra tutor. And in this section, we're going to tackle the topic of what we call exponents in algebra. You also might hear them referred to as powers. So the title of the section is Powers and Exponents. So up to this point in our journey to study pre-algebra, we've learned some very, very important things. We've learned about the concept between negative and positive numbers. And so now we're going to begin to get, I think, a little bit more into the realm that you might actually associate with pre-algebra or an algebra class. And that is, a lot of times students open a book and they'll see a bunch of stuff on the page. Of course, the variables x and y a lot of times confuse people. We've sort of broken down those barriers a little bit already so far. And the exponents a lot of times scare people because it's something different that you really haven't had to deal with in your basic math. It's something that looks a little different. You've got a little number up there raised a little bit higher. What does that really mean? And so a lot of students just try to memorize rules to get by without really understanding what they are. And I promise you, if you just understand what an exponent is, it's not a big deal. It's going to be something that's going to be very easy. And once you can master that, then moving along into the other topics is going to be so much easier. So let's talk about powers and exponents. The number one thing to remember is the term power. When you raise something to the power of 2 or to the power of 5 is exactly the same thing as when we talk about an exponent. They're not different from one another. So some books you might see them refer to raising something to the power of 3 or to the power of x or something like that, raising to a power of. And some other place in the book you might see it written as the exponent 2 or the exponent 5. Well, the word power and exponent really, for the purpose of this class, are really interchangeable things. And so we're going to treat it that way. So power and exponent is the same thing. So what is an exponent? What is a power when you raise something to a power? The short answer is writing an exponent is a short way of multiplying things together. Okay, when they're multiplied by itself. So it's just like back when you learned how to multiply numbers, you were taught multiplication is a shortcut for addition. You know, 5 times 4 is 20. That's a short way of adding up a bunch of stuff, right? Well, when you have a number multiplied by itself a whole bunch of times, it's actually faster and easier to write it as an exponent. So writing it as an exponent is just a shortcut for multiplication, much like multiplication is a shortcut for, addition. So it's a very simple thing. Now let's talk about it, and let's find out what this exponent stuff really is. If I have the number 3, let's say, and I'm going to raise number 3 to a power or to an exponent, same thing, of 2, right? So I write it as 3 squared. That's how you write this, because anything with a power of 2, we call it squared. But you could just say 3 raised to the power of 2. Couple of quick definitions that you might be asked on your tests. Not something that you use every day in your algebra calculations, but this bottom number, the bigger number here, is called the base. The reason it's called the base is because it's the bottom number, and also it'll make a little bit more sense when we write it out why it's called the base. This top number here is just exactly what we talked about a minute ago. This is called the exponent. So the only reason I'm even telling you this is because on your test you might see things like, what is the exponent in this problem? Or, identify the base in this problem. Or if two numbers have the same base, then what's going on here? So you're going to need to know what these terms are, but in your everyday calculations, you're going to get so used to dealing with these things that you're not going to really have to memorize this too often. Now, what does this mean when you say 3 raised to the power of 2? It's very simple. What it means is, literally for this problem, it means 3 times 3. And that's it, folks. I mean, that is the definition of an exponent by way of an example. You see, if I have 3 and I multiply it by itself, I can keep it on the paper just like that. That's no problem if I want to. I can say, there's nothing wrong with saying 3 times 3. We know the answer is 9, right? We know the answer is 9. But it might be simpler in a lot of cases to just write it in a shorthand way. So that's why I was saying that exponents or powers is just a shortcut way of writing down what you already know how to do, which is multiplication. It's really nothing more than that. It looks a little funny because you've never had to deal with it before. You've never had to learn and use it before. But it really is no more complicated than multiplication. So we write it like this. 3 is the number that you're multiplying by itself, and the upstairs number, number 2, is how many times 3 is multiplied by itself. How many times it's multiplied by itself. So anytime you see an exponent, what you've got going on is some number or some expression multiplied by itself. It has to be multiplied by itself this many times as given by the top number. So you're never going to have, different numbers, 3 times 4 and write that as an exponent. It has to be multiplied by itself in order to be able to write it as an exponent. And of course, the answer to this is just simply 9. So you might say to yourself, why would I even do that? Why wouldn't I just write 3 times 3 is 9? Well, you're just going to have to trust me a little bit here. When we get farther into the course, maybe we're not dealing with 3 times 3. Maybe we have x here or y here or something else raised to the power of 2. So this exponent stuff may not seem like it would be something you would use a lot when it's written like something simple like 3 times 3, but as we get into more complicated problems, it's something that you're going to use all the time. Okay, so let's go and just get our feet wet with a few other problems. Let's say we had the number 10 raised to the power of 3. 10 raised to the power of 3. What would that mean? Well, it's the same exact thing. When we have something like this, the base number is what's actually multiplied by itself. So it's 10 times 10 times 10. How do you know how many times to multiply 10 by itself? Well, that's given by the top number. So we multiply it 1, 2, 3 times. That's it. So 10 times 10 is 100, and 100 times 10 is 1,000. If you actually have a scientific calculator, if you take 10 and raise it to the power of 3, the calculator internally is going to do this multiplication, and it's going to spit out the number of 1,000. 10 times 10 times 10 is 1,000. Because 10 times 10 is 100, and multiply one more time, times 10 is 1,000. So, but it's the same thing. We've got the base here, 10, multiplied 1, 2, 3 times. That's given by the top number. What if we had, and we're going to do a ton of problems. I'm just giving you some really sort of basic ones here to get your feet wet. What if you had the number 7, and we're going to raise that to the power of 4. We're going to raise that to the power of 4. So, if you were going to do that, what would you have here? Well, you're always multiplying the base. So it's 7 times 7 times 7 times 7. You do it 1, 2, 3, 4 times because that's the number given in the top. And you could take 7 times 7 times 7 times 7, and you could put that in your calculator, and that would give you a number. That would be the answer, which is exactly the same as if you took 7 and raised it to the power of 4 in your calculator. So you see, literally it is a shortcut for multiplication. There's nothing else going on here magical. We haven't even used any x's or y's or anything that looks like algebra. We just sort of introduced this concept of an exponent. But you're going to see, as we go into subsequent sections and talk about equations and other things, that you're going to see these exponents pop up all the time. So it's very important for you to get comfortable working with them so that you're not worried about them. You're not struggling with trying to understand what that is. You've got that, so then you can go on to the other topics. All right, so let's talk about something a little bit more complicated. This is the basic idea of what an exponent is. Now, what happens if we try to multiply two things that have a power in it together? So let me draw a little line here, right? And let's say, let me write it in a different color. I'm going to put a little asterisk here because you're going to need to remember this. When we multiply two terms with, that's what this W means, with two terms with exponents that have the same base. That's why I introduced the terms before. So now you know the base is the bottom number here. When we multiply two terms together that have exponents and that they have the same base, then what we do in that case, I'm going to actually change colors to make it a little bit easier to read. We add the exponents. All right, so this is sort of one of the rules that you learn in algebra. It's just one of those things, like when you learn how to add numbers, you learn how to take, and add them together and you get a number. Well, when you're talking about multiplication of numbers that have exponents, you have to learn a few rules. They're not hard. I promise you they are not hard. But let's take it by example. Take a simple one. Let's say you had 2 raised to the power of 3, so 2 cubed, and you're multiplying this by 2 squared. So in a test, or maybe in an equation somewhere, you might have literally 2 raised to the power of something. In this case, it's 3. Here, this is 2 raised to the power of something. In this case, it's 2. Well, what this rule is telling you is if we're multiplying these things together and they have the same base, which they do in this case, 2 is the same base, then all you do is you add the exponents together. So the answer here is 2, and you take 3 plus 2. So you say 3 plus 2 in the exponent. So that's 2 raised to the power of 5, and that's the answer, 2 raised to the power of 5. You don't have to write this step here. If you can just add these together, that's fine. You can write it down, but I'm just doing it here to show you explicitly what's going on. So that is the rule. We're going to use this rule a lot in this section, but if you have numbers that you're, or exponents that you're multiplying together, they have the same base, then all you do is add the exponents together to get the final answer. And the base is the same, notice that. Now, if the bases are different, we'll do some problems in a second, but let's say this is 5 to the power of 3, multiplied by 2 to the power of 3. You can't simplify it anymore. You can't do anything to it because they're different bases. The rule is that they have to have the same base. Now, you can simply memorize that rule, that's fine, but I would like to tell you why that's the case so that you don't just think algebra is a set of rules that don't seem to make any sense. It makes perfect sense why you're only allowed to do it if the base is the same. And to do that, you have to understand what we talked about before. Right here, what would we do if we were going to write this down? This would be 2 times 2 times 2. That would be this guy, right? That would be 2 raised to the power of 3. 2 times 2 times 2, multiplying it 3 times. Now, if we wrote this guy out separately, like this is 2 squared. So he's 2 times 2. So this term right here is 2 times 2 times 2. This term is simply 2 times 2. And they're both multiplied together, so there's another kind of multiplication symbol in the middle between them because this is multiplied by this. So you see, if the bases are the same, this is exactly the same as 2 raised to the power of 5 because 1, 2, 3, 4, 5. See, the number 2 is multiplied by itself 5 times. So that's why we add them together, because when they're the same base, we end up counting them in the end to make the new exponent, and so we're able to do that. If this were 5 raised to the power of 3, then it would be 5 times 5 times 5 times 2 times 2, and then I wouldn't be able to simplify it anymore. I certainly couldn't add the exponents because they're going to be completely different bases. So it doesn't really help me to do that. I'm not allowed to simplify it because they're different. It would be like comparing a pencil to a baseball bat. I mean, they're just different things. You can't, I mean, yeah, you can count pencils and baseball bats, sure, if you have a bag of them, but it doesn't really make sense to put them in the same bucket and say that they're the same thing. In this case, I'm talking about the base of 2. So I can deal with the exponents like this, no problem, because it's really the same thing in shorthand notation. But if I have 10 raised to the power of 3 here, then this is 10 times 10 times 10, and there's no way I can really write that as a single exponent because the bases are different. So that's why when you multiply numbers with the same base, you can do that. Now let's go on to another guy, just as another quick example. Let's say we had 8 squared times 8 squared. 8 squared times 8 squared. So how would we do that? According to the rule, they have the same base. So all I need to do is write a number 8 and then add the exponents. 2 plus 2 is 4. I just add the exponents. And again, the reason why this works is because this can be written as 8 times 8, and this also can be written as 8 times 8, and they're multiplied together. So in the end, I'm just counting 1, 2, 3, 4. They're all multiplied together, so 8 raised to the 4th power. If this was a different base, it would be a totally different problem, and I wouldn't be able to combine them like that. All right, number 3. Let's say I have 2 cubed multiplied by 5 squared. What do we do there? Well, we look first to see, okay, are the bases the same? The answer is no, the bases are not the same, so there's nothing else I can do. I just write something like fully simplified already. Just to tell you that we've looked at it, this is completely different. This is, if I were to break it out, 2 times 2 times 2. This guy is 5 times 5. So if I wrote this, this would be 2 times 2 times 2 for this guy, and this guy would be 5 times 5. Now they are all multiplied together, but I can't simplify it into one exponent because the bases are different. So, you know, I can't just count them all up and add them because they're different. Okay, so that's the sort of the rule that you need to know when multiplying exponents, numbers that have exponents together. If the base is the same then you can simply add the exponents. It doesn't matter what the base is, but if the base is the same, you can add the exponents. Now, similar rule, it happens if you're dividing numbers with exponents. So let's talk about that. Let me switch colors here a little bit. Okay. Put a little star here so you'll remember this. When dividing terms with exponents that have the same base, and I'm going to switch colors so that it stands out what we're going to do. In that case, we simply subtract the exponents. So I know it looks like a bunch of rules, but really there's a lot of symmetry here. If you're multiplying them together and the bases are the same, you add the exponents. If you're dividing them and the bases are the same, then you subtract the exponents. So if you're multiplying, you add exponents. If you are dividing, you subtract exponents. Only if the bases are the same in both cases. If the bases are different, there's nothing you can do. You can't simplify that anymore. So just to give you sort of an example of this case, what if I had 2 raised to the 4th power divided by 2 raised to the 2 power, 2 squared? Well, I look and I say, well, the bases are the same, so I should be able to do something here. And all I have to do is write the base down. The base is always going to be the same, and I subtract the exponents. 4 minus 2. So that's going to be 2 raised to the power of 2. You always start at the top and subtract off the bottom exponent. That's the way you do the subtraction, top minus bottom. So this is 2 squared. Now, we should at least once figure out why this works. So let's rewrite this here. 2 raised to the 4th power, what would that be? 2 times 2 times 2 times 2. That's 2 to the 4th power, right? Divided by 2 squared. 2 times 2, right? 2 squared. Now, we're going to talk about this a little bit more, but if you think about it for a second, all of these numbers are multiplied on the top, and all of these numbers are multiplied on the bottom. So if you notice here, all of these 2's are multiplied in the top, and all of these 2's are multiplied in the bottom. And so, you know, when you think about it, 2 divided by 2 is 1, so this can sort of cancel out with this. It doesn't really disappear, it's just that when you do this division there, it's going to be equal to 1, so they're going to effectively disappear. This 2, for the same reason, can cancel with this one. This is sort of a general rule that you're going to need to understand. We're going to talk about it as we work more into pre-algebra. Anytime on any fraction at all, if you've got stuff multiplied in the top and multiplied in the bottom, and you have the same term in the top and the bottom, just like we have a 2 here and a 2 here and a 2 here and a 2 here, you can just strike them out because they, in effect, are not going to matter. So in the end, what we're going to have here is 2 times 2, which is 2 squared, which is what we got for our answer, which is going to be 4. So make sure you understand that. We're going to talk a lot more about cancellation you know, as we start to work more with fractions later, but really it's no different than, you know, what if you had the fraction 3 divided by 3? What would that equal to when you take 3 divided by 3 in your calculator? Well, that's equal to 1, right? Well, what if I had, just as another example, 3 times 3 divided by 3 times 3? Well, you know that I could do 3 times 3 and I could get 9, and I could do 3 times 3 and I could get 9 on the bottom, and you know that 9 divided by 9 is big fat 1, so you know the answer is 1, and that is one way that you could do this problem. But another way that you could do it is just to recognize, look, in this original fraction, I have a lot of stuff common to the top and the bottom. 3 can cancel with 3, they're going to divide out. This 3 can cancel with this 3, and they're going to divide out. So what I'm going to be left with, 3 divided by 3 is 1, 3 divided by 3 is 1, you know, all you have is 1, so the answer is going to be 1. It's just trying to show you, by way of an aside example, that anytime you have numbers or x's or y's or anything in the top of a fraction, and you have also the same thing in the bottom of a fraction, and all the stuff is multiplied together in the top and the bottom, then you have free will in order to just strike them out. So when we do that for this process, we see that the subtraction works. And the reason the subtraction works is because what I have here in the top is 2 extra 2's than what I had in the bottom. So I can simply they all disappear, because when you divide them, they're going to effectively go away to 1. What I'm left with is really what the answer is going to be. But you don't have to think about all that. That's just to give you an idea of why it works. This is the real rule. If the bases are the same, you subtract the exponents. So what else do we have? Let's say we have 8 raised to the power of 5 divided by 8 raised to the power of 4. So here we have the bases are the same, so all I do is subtract the exponents, 5 minus 4. So I'm going to have 8 raised to the power of 1. And you know 8 raised to the power of 1 is just simply 8, because it's multiplied by itself just one time, so that's just the only thing there. Okay, and if you were to take 8 to the power of 5, and you would have 5 8s on the top, and you would have 4 8s on the bottom, and you would get a bunch of cancellations, and the only thing that you would have left over would be the 8 on the top, and that's why that rule works. So for one final quick little example here, what if you had 10 squared divided by 10 squared? Well, the bases are the same, so you just subtract 2 minus 2, top minus bottom, and you'll get 10 raised to the 0 power. Now, one thing I didn't tell you yet that you're going to need to remember, anytime you have anything raised to the power of 0 to 0, and no, it doesn't make sense at first, but that is by definition always equal to the number 1. Number 1. That is a mathematical definition that doesn't seem to make a lot of sense when you take 10 and raise it to the power of 0, why you would get 1, but it is a definition. It's a mathematical thing that's given to you. You just need to remember it. The details of why they define it to be like that is just something that I don't want to get into. It doesn't really help you any. It's really just something mathematicians have said, okay, we're going to have to make this definition to make everything else work. So when you have anything raised to the 0, it could be anything, 900 million raised to the power of 0. It could be x, 10x raised to the power of 0. Anytime you have something raised to the power of 0, you're going to get a 1. It's by definition. All right, so I think we have a good overview. We know basically what an exponent is. We know that when you multiply exponents, if the bases are the same, you add the exponents. We know that when you divide exponents that have the same base, you subtract the exponents. So what we're going to do right now is we're going to do some problems. A ton of problems, actually, to get you comfortable. And I promise you that by doing it over and over, you guys will get really good at this. So for this first set of problems, let's write it. Let's write the following as an exponent. Whoops. As an exponent. Okay. So the first one is 10 times 10 times 10. How do you write that as an exponent? Okay, well, you have the same number here, so you write it as 10 cubed because you're multiplying itself 3 times. That's why you write the 3 up there like that. Number 2. What is 9 times 9? How do you write that as an exponent? You got the same number here, so you write 9, and it's going to be raised to the power of 2 because you're multiplying it by itself 2 times. These are going to be a little bit fast, but you guys will get the hang of it by doing it. What if we have 7 times 7 times 7 times 7? If we're going to write that as an exponent, it's 7 raised to the power of 1, 2, 3, 4. And it's a shorthand way of writing that multiplication. What if we have 5 times 5 times 5 times 5 times 5? Base is all the same, so we take 5 and raise it to the 1, 2, 3, 4, 5. We're at 5 raised to the power of 5. Now let's switch it up just a little bit and say b times b. Now don't get so worried if you see a letter in algebra or pre-algebra. It doesn't mean anything special. It just means this is a number. I just don't know what the value of it is. Maybe b is some variable, something I'm solving for. Maybe it's the base of a house or something I'm solving for. But for right now, just think of it as a placeholder, but the exact same rules apply. It doesn't matter if it's a letter or if it's a number. The way you write this is you look and you see, well, I've got the same base here, really. So I just say b squared, because there's 2 of them, multiplied by itself 2 times. So you treat it exactly the same way. What about c times c times c? Same thing. Same base, which is the letter c, which is some variable for something, multiplied by itself 1, 2, 3 times. So I just put it like that. What if I have x times x times x times x? You're going to see a lot of x here in algebra. The base is all the same. It's basically the same thing multiplied by itself 1, 2, 3, 4 times. So you see the pattern. There's nothing magical about this. It's just being comfortable with it. What if we had y times y times y times y times y. We don't know what y is. Y is just a letter that's a placeholder. But everything is the same multiplied by itself 1, 2, 3, 4, 5 times, so that's what we mean by that. Now, what if we had 5 times 5 times a times a? 5 times 5 times a times a, how do we write that? The way we write this is 5 times 5. This is the same base here, so I can write this as 5 raised to the power of 2, like that. And then it's also multiplied by a times a, which is a squared, because a has two of these a's multiplied together, a squared, like that. So 5 squared times a squared. And another thing that you can sort of think about doing this another way is, if you want to get a little bit more fancy, you can rewrite this as 5a times 5a. You should be able to convince yourself that this is really the same thing. Whoops. You should be able to convince yourself that this is really the same thing, because I could take this 5a and put it here, and I could take this 5a and put it here. They're still multiplied together, so I can rewrite this, if I want to, as 5a squared, because this is multiplied by this 2 times. So the base is 5a multiplied by itself twice. So these two things here, these are exactly the same thing. 5 squared times a squared is the same thing as what we have here. We're going to do a lot more work with exponents in the future. I'm going to teach you that this is a rule that you're going to use a lot here, but I'm sort of giving you a little bit of a preview. These are the same thing. What about 10? You have, let's say, negative a times negative a times y, right? So you can do it a couple of different ways. Just for practice here, let's say we can do, this is negative a times negative a, so I could say this is negative a squared, and this is y times y, so I can say this is y squared. And I can do that because these guys are the same base in there, and this guy is the same base, which is what I have over here. Okay, now let's say, let me go back up to the top here and give myself a little bit more room. What if I have, for 11, what if I have negative 3 times negative 3? Negative 3 times negative 3. So it's the same base. Negative 3 is the same in both cases. You need to be careful and put it inside of parentheses here, though, because if you don't use the parentheses, it'll be confusing. If you just simply write it as negative 3 squared, then the person reading your homework is not going to really know, well, the way you really read it in algebra is 3 squared with a negative out front. You're not trying to do that. You're trying to say negative 3 is multiplied by negative 3. So you want to make that clear by wrapping it up in parentheses. If you write it like this, somebody might, they might interpret it this way, but some other people might say, well, this is negative 3 times 3. The 3 squared being here and the negative just sitting out in front. So in order to avoid this confusion here, if you just kind of leave it hanging out there, and if you really mean the negative to be on the inside, then you really need to write it like that. Because if you don't, you're just going to get people confused. Okay. What if we have, for the next problem, negative 3 times 3? This is a great example of what I'm talking about here. If you want to be clear about this, the best way to do it is write it as negative on the outside, 3 squared. Because this is going to give you what you want. The negative is just sitting there. 3 times 3 is really what the exponent is. That's what I want to square. You can also write this, as I said just a second ago, by negative 3 squared, and most people will interpret it the right way, which is 3 is the thing that's squared. The negative is just sitting there. But you can also accidentally interpret it like you have up there. So it's better to use parentheses to make sure that the person knows that the square applies to what we have in the parentheses there. 13. Let's say we have negative 6 times negative 6 times negative 6. Okay, so negative 6 is clearly what we're multiplying together, so we'll just stick that inside of the parentheses and we'll cube it, just like that. And then our final problem of this type, let's say we have negative b times negative b times negative b times 2 times y. So clearly these things are just out there. I can't do anything with them, but these are all multiplied together with the same base. So I can say negative b cubed times 2y. 2y being just left along for the ride on the outside. So this is great great work and great practice with just writing exponents. Just getting practice writing them, multiplying them, getting the exponent off by itself, and taking care of your negative signs. Now what we're going to do here now is we're going to do the reverse. Let's give you some exponents and let's let you write them out. Okay, so let's go ahead and write as an exponent. Let's write as a product of terms. So we're going to do the reverse here. We're going to have an exponent like 1 raised to the 4th power, and we're going to write it out. So base is there, so it's 1 times 1 times 1 times 1. You multiply it 4 times because of the exponent is a value of 4 up there. Okay, what if you have 4 raised to the power of 6? How would you write that out? Well, this is the base, so it's 4 times 4 times 4 times 4 times 4 and times 4. 1, 2, 3, 4, 5, 6, because I've got a 6 in the exponent. That's telling me how many times to do that multiplication. Okay, what about b cubed? Same sort of thing. This is the base. Doesn't matter if it's a letter or not. B times b times b. 3 times. All right. And what if we have negative 10 raised to the power of 4? Now there's no parentheses here. So you got to be careful. The way you do this is, since there's no parentheses, the negative just hangs out there in front. What I'm actually raising to the power is just the 10. So it's 10 times 10 times 10 times 10. 4 times because of the power up there. Now if I had written it differently, negative 10 raised to the power of 4, everything is inside the parentheses. That is the base. So here I would have negative 10, whoops, got to write 10 correctly, negative 10 times negative 10 times negative 10 times negative 10. So you see it's clear because it's all inside the parentheses that the negatives are carried throughout. This is going to give you a different answer than this because of the negative signs. So carrying that a step further, what if I had negative s cubed? Well, there's no parentheses here, so the negative is just hanging out in front. What I'm actually cubing is the s times the s times the s. That's what I'm actually cubing, so that's how you would write that. But if I had instead written it as negative s cubed, then it would be a different answer. It would be negative s times negative s times negative s, because the negative s is what I would be multiplying by itself 3 times. So here we have a great set of problems that shows you how to go in reverse. It's really the same exact skill. We're just going the other direction. Just be careful with the negatives. And it's a very common thing on a test. If you see the negative inside of parentheses, then you have to carry that through your multiplication. If it's just sitting by itself, then this negative is just like a negative 1 sitting out here. And what you're actually doing the exponent of is what's left over. Now what we're going to do is really along the same lines. How would you on a test, how would you, let's say you were going to do a problem like, let's say we're going to say evaluate 2 raised to the power of 3 and evaluate that number. Well, you would have to know that that was the same as 2 times 2 times 2, right? And when you do this, well, 2 times 2, that's going to give you 4, but you have to still multiply by 2, and that's going to give you 8. So when you're evaluating these guys, you're going to have to take your time. 4 cubed, right? So that's 4 times 4 times 4. 4 times 4 gives you 16, but you still have to multiply by 4. 16 times 4 is going to give you 64. And so that would be the number that your calculator would spit out at you. If you had 1 raised to the 4th power, anything with a 1 as the base is easy because it's 1 times 1 times 1 times 1. And you know that if you multiply by 1 enough times, you're just going to still get a 1. Okay. Now let's say you had negative 2 raised to the power of 3. So you would have, just to keep it clear, negative 2 times negative 2 times negative 2. 3 times because of the cube. Negative 2 times negative 2 is positive 4, but you still have to multiply by this negative 2 here. 4 times negative 2 is negative 8. Because of the rules of multiplication that we studied in the last section. Negative times positive is going to give us a negative all the time. Okay? And what if we had something like, a little bit tricky, let's say negative 3 squared. Well, it's the same thing. The negative's hanging out front. The 3 times 3, which is what the exponent represents, is just sitting here. So we're going to have negative 9 because 3 times 3 is 9. The negative is just hanging out in front, right? And so that's basically a good little set of problems to show you how to do that. Basically, you just need to do exactly what we did before in the previous section, but then be really careful multiplying as you go left to right and keeping everything straight. See, I wrote this step as an intermediate. Negative 2 times negative 2 is 4 times the negative 2. If I were to just try to do it all in my head, I would probably make a mistake. Now let's go and let's simplify. Let's simplify the following expressions. And we're going to need to use basically our rules. What if we had 3 raised to the power of 7 times 3 squared? Well, yeah, we can multiply all these out and figure it out, but we know the base is the same. So we just add the exponents. 7 plus 2 is 9. That's the answer. What if we had 2 to the power of 5 times 2 to the power of 5? Well, the base is the same, so we just add the exponents. 2 to the power of 10. 5 plus 5 is 10. What if we have 3 multiply by 3 squared? Well, the base is the same, so 3. And you have to remember that when you have a whole number, you have an implied power of 1 there all the time. So this little invisible 1 here added with 2 is going to give us power of 3. Now what if we had 5 squared times 6 squared? How would we do that? Well, we can't do anything here. We can't simplify it anymore because these are different bases. So this is 5 times 5 and this is 6 times 6. So there's really nothing we can do. It's not saying it's wrong to do the multiplication here. It's just saying that I can't make it any simpler. Here I'm simplifying this into something easier. What if I had 6 cubed times 7 squared? Well, there's nothing I can do there. The bases are not the same. Right? Now, what if I had, just to show you that it really doesn't matter, what if I had x cubed times x to the 4th? Well, the bases are the same. X, 3 plus 4 gives me 7. It doesn't matter if it's a letter or a number or anything else there. It just matters that the base is the same. What about y squared times y squared? Well, the bases are the same, so it's y, 2 plus 2 is 4. So we're just exercising our rule. When the bases are the same, we add the exponents. Now what I want to do now is give you some practice in doing exactly the same thing, but when we're dividing these things that have exponents. So what if I had 8 to the power of 6 divided by 8 to the power of 5? Well, I have the same base, so I just put that base down and say 6 minus 5 is 1. And that's the answer. Of course, anything raised to the power of 1 is just the number itself because it's multiplied by itself, just the single time that you write it here. What if I had 10 raised to the power of 10 divided by 10 raised to the power of 7? Well, the bases are the same, so I just subtract. 10 minus 7 gives me 3, so that's how I simplify that. What if I have 12 to the power of 15 divided by 12 to the power of 14? The bases are the same, so I write the 12 down. 15 minus 14 is 1, and so anything to the 1 power is really just itself. Now, to switch gears a little bit, let me switch colors. What if I had 10 raised to the power of 2 divided by 7 raised to the power of 2? Well, yes, I can put this in a calculator and get a number, but I can't simplify this anymore because this base is different than this base. So I can't do anything. I can't do anything to simplify it anymore. I can calculate the answer, sure. 10 times 10 on the top and 7 times 7 on the bottom, and I can divide and get a number. I just can't simplify that anymore. Now what if I have a cubed divided by a? A cubed divided by a. Well, I have the same base, so it's going to be a. 3 minus 1, because there's an implied 1 here, 3 minus 1 gives me 2. Let me go up here to give me a little bit more room. What if I have b raised to the power of 7 divided by b squared? Well, I have the same base, so I write that down. 7 minus 2 should give me 5, so I'm going to have b to the power of 5. And finally, what if I have s to the power of 4 divided by a to the power of 3? Well, these are like apples and oranges, different bases, so there's nothing I can do. I cannot simplify this anymore. A lot of times in algebra, what you're really trying to do when you solve an equation or something like that is, in the end, you're trying to simplify your answer. Just like simplifying a fraction from, from fourth grade. You know that 4/8 is the same as 1/2, and you're taught how to simplify it. Well, these things, dealing with the exponents and how to add them and all, it's really just teaching you how to simplify algebraic expressions. Because later on we're going to get to more complicated expressions, and you're going to know that if the bases are the same, you just add the exponents. It makes it simpler. If your bases are the same here, you subtract the exponents if you're dividing. So those are important things to do. They're very core central things in pre-algebra. You'll use them in Algebra 1, you'll use them in Algebra 2. You'll use them forever, basically, from here on out. It's the bedrock of math in the algebra realm. So I'm Jason. I hope you've learned something. I hope from the examples you've gotten a really great feel for how to do this. Watch this section a second time if you need to. It will get better with practice, I promise you that. And give yourself a lot of practice and a lot of time. Get yourself comfortable with this stuff, and then I promise you the future sections will come that much easier for you.